We talked about linear and volume changes in fluids and solids with temperature in the previous video. With gases, it's a little more complex because gases behave a bit differently since they're fluids, but they usually expand to fill the container that they're in, right? They're fluids in the strictest sense that they flow. But unlike liquids, gases will expand to fill whatever space they're in. So for example, if you could make the room you're sitting in a perfect vacuum, and then you brought in a helium balloon and popped that helium balloon, the helium in that balloon would quickly increase to fill the vacuum space. Liquids don't do that. If you spill a liquid in a vacuum, actually it probably will evaporate and become because there's zero pressure, it will evaporate and become a gas and then fill up the room. But liquids don't automatically fill up the space that they're given like gases do. For example, again, the gases in the room you're currently sitting in there's no place in the room you're sitting in where there are no gases. So we can talk about volume changes for gases using what's called the ideal gas law. Now, this ideal gas law is just that. It works ideally or for ideal gases. What is an ideal gas? Well, it's a gas where the atoms are molecules. So some gases are atoms, like helium. It's just one little helium atom bouncing around, hitting other helium atoms. Or gases can be molecules. Think of O2, oxygen. Oxygen can be a free atom bouncing around, but in our atmosphere, it actually bonds to form O2, N2, nitrogen, CO2, a gas molecule, H2O, water vapor, can be a gas. So these molecules interact with the walls of the container and with each other via elastic collisions only. So we think of them as tiny little indestructible pool balls bouncing around and hitting one another and hitting the walls of the container. And that's the only force acting in the sense of an ideal gas. Now, in chemistry, you probably learned about like van der Waals forces and things, where you can have weaker interactions because molecules and atoms have electron clouds. They can interact electromagnetically with slight attraction and things like that. But we're going to pretend that doesn't happen. And the temperatures we're dealing with, kinetic motion and elastic collisions by far dominate the properties of these gases. Weaker forces are only present when you cool a gas down to near absolute zero. So the ideal gas law is given by the following equation. There are 5 terms, and I've defined all the terms here, but we'll walk through them. The pressure times the volume of the gas is equal to N, the number of atoms or molecules you have in that gas, times this term K sub B, a lowercase k sub B, which is Boltzmann's constant. It's a constant that allows all these terms to SI units to work together. And the temperature in kelvins. Now note that this is not delta T. This is just T, the temperature. Whenever you see just a T in physics, assume Kelvin. Right? Don't use Fahrenheit, don't use Celsius here. Delta T, the change in Celsius degrees, is the same as change in Kelvin. Those two values are the same. So delta T, kelvins and Celsius degrees can be interchanged easily. That's why the Kelvin scale was designed the way it was. Temperature, absolute temperature, Kelvin and Celsius are not the same value. So you must use kelvins here. So Boltzmann's constant, given here below, is 1.38 times 10 to the minus 23 joules per Kelvin. So when you plug in Boltzmann's constant on the right, N is just the number of atoms or molecules. That's just a count, so that has no units. Temperature is Kelvin, so you multiply Boltzmann's constant by temperature in Kelvin, you end up with the right-hand side just being joules or energy. Well, if this is the right-hand side of this equation is joules, the left-hand side of this equation also has to be joules. And you can actually calculate pressures in pascals, which is newtons per meter squared. Volume is in meters cubed for SI. If you cancel those units, you find out that, indeed, joules is actually on the other side as well. So this is the ideal gas law. It allows you to determine, for gas of a specific number of particles of a specific temperature. If you know the volume of the container, you can figure out what the pressure is on the walls of that container, what the pressure of the gas is. Or if you have a pressure and a volume, you can determine the temperature. So if you think about it, this is kind of interesting how bike tires work. If you've ever pumped up a bike tire, the volume of gas in that tire is the same, right? The inside tube of your tire doesn't change volume. I mean, unless it's completely flat, it might move up a little bit, but as you're pumping toward the end, the volume doesn't change. The pressure is increasing because you're adding more molecules. You know, that's what you're physically doing. You're shoving more gas into those tires, which increases the pressure. Now, this form of the ideal gas law, chemists might not be that familiar with. Now, here, this is a capital N. That's just the total number of atoms or particles. Chemists use moles. Remember, mole is an SI unit. So we will talk about this a little bit later in the video. We'll recast this equation using moles and the gas constant. But first, I have to introduce what moles are. A mole is related to a number called Avogadro's number, where 1 mole is equal to 6.02 times 10 to the 23 objects, right? A mole can be a mole of anything, a mole of oxygen molecules, a mole of automobiles, a mole of stars. A mole is just a quantity of something. Technically, by, again, very explicit SI definition, Avogadro's number is the number of atoms in exactly 12 grams of carbon-12. Now, carbon is an atom that has different isotopes. You can have carbon-14 for radioactive dating. You've probably heard of carbon-14 dating. Carbon-12 is the most common stable form of carbon. If you have a pure sample of carbon-12 and you have exactly 12.000000, exactly 12 grams of carbon-12, you will have Avogadro's number of atoms in that 12 grams. Well, why do we use moles? Why do chemists use moles? Well, a mole is a more apt or apropos quantity for doing chemistry experiments, right? 1 gram of carbon-12, 12 grams of carbon-12 is 1 mole, right? 12 grams is something you might use in an experiment in chemistry class. 1 mole of carbon or some fraction or multiple of 1 mole. It's much, much easier than dealing with the fact that this is almost a trillion objects, right? This number becomes so large that it becomes nonsensical, right? It becomes non-intuitive. Whereas moles, for a chemistry experiment, is more intuitive. You've probably done chemistry experiments if you've had a chemistry class where you count how many moles of a substance you make, or you estimate how many moles of your product. That is something more hands-on and more apropos to a laboratory setting. So, recasting the ideal gas law using the number of moles of a gas, we get the following equation. Pressure times the volume is equal to the number of moles, and is the number of moles, times this constant R, which is called the gas constant. It has a value of 8.31 joules per mole Kelvin, times temperature T, again in kelvins. And you know you have to plug temperature T in Kelvin because the gas constant has kelvins in it. The only way this kelvins is going to cancel in this equation is if your temperature is also in kelvins. The only way that this mole is going to cancel is if N is in moles, and the value will cancel. So you can see that this is very similar. PV equals nRT is very similar in form to PV equals NK sub B times T. Right? The only two things that differ are these two values here. So for this equation to work, these two terms, the number of moles times the gas constant, must be equal to the number of particles times Avogadro's number. And that's a pretty easy thing you can punch into your calculator and verify. So this is the ideal gas law you use when you're working with moles. The other one is the ideal gas law you work with when you're dealing with number of molecules. And of course, once you figure out the number of moles, if you want the number of molecules, just use this conversion factor. 1 mole is this many molecules. So if you have 1 mole of a substance, you have 6.02 times 10 to the 23 molecules or atoms of that substance.